Hello, everybody. Today, unless anybody has specific topics they want to go over, I plan to talk about improper integrals. We won't go too deep into them. There's a lot more. I'll say we'll introduce them. I'll say, but I want to kind of give more of a theoretical understanding of what improper integrals are, why they make sense, how do we deal with them, that sort of thing. Again, there'll be a lot more to actually dealing with them properly that we can talk about. But this is what I want to kind of go over. This is what I want to kind of go over for this. So basically, the idea. Let me start off. Let me start off with this. If I share my screen real quick, just let me know when this comes through. Cool. So basically, what I'll say about integration by part, or sorry, not integration by parts, improper integrals. So you already know what an integral is. Obviously, we've been talking about that for the last couple weeks. But what makes it improper? That's the question. So what makes it improper as opposed to a normal or proper integral? Basically, the thing that makes it different, I'll say, is I guess how should I word it? Basically there's an infinity somewhere. That's what makes it an improper integral. So like an infinity shows up somewhere, and what do I mean by somewhere? Either the input or the output. So normally when we integrate functions, there's no infinity involved. It's just normal area under the curve, and that's fine. When there's either an infinity in the input or an infinity in the output, then it becomes improper. So, and just to reiterate, so we usually call these type one improper integrals. Improper integrals. This would be like infinity in the input, and then we have a type two improper integral. So type two, I'll say improper integral with infinity in the output. So infinity in the output. Now, what will these look like? And you'll probably see if you're going over this section in class right now, what will these be? Basically, if you take this, it'll look something like this. Maybe I'm just making this up, but I'll say one over x squared dx. That would be a type one improper integral because you can see one of the bounds. Again, these are the input, right? These are the bounds on x. One of the bounds is infinity. So one of the bounds you can see we have an infinity in the input. That's what I mean by that. One of the x bounds goes to infinity rather than a finite number. And then over here, another one, I'll just give another example. You could also have the lower bound like going to negative infinity. That's also possible. And let's say it goes to like, I don't know, negative three. And then let's say one over, I'll just use the same function just to make it easy. It could be a different function. These would both be examples of type one improper integrals. Now, to be honest, I think type one is easier to, I think it's type one is objectively easier to deal with than type two. I'll say that. Um, Basically, for one, it's obvious that they're improper because we see an infinity. Like if you see infinity or negative infinity in the problem, it's improper for sure. What's a lot sneakier is something like this. I'm just making this up. This would be like from negative one to one of, let's say, yeah, let's just use the same function for make it interesting. This one is a type two improper integral. And it might not make sense why yet, but let's actually test this out before diving in. If I go into these, if I actually try these, let's see. If I actually do in Desmos, you can do this, right? If you just start typing int, that'll be the integral. And then you go from one and then one to what, you can literally type in the words infinity, and it should turn into an infinity symbol. So Desmos makes it easy. And then basically if I just go one over x squared dx, you can see this is kind of a weird idea, and we'll talk about how this is even possible because it probably doesn't make sense right now. But we have an infinity in the input. Like our width is infinite in this problem, and yet we still have an answer that makes sense. And then you could do this other one too, like this other one. What did we say here? We said negative infinity to three or negative three. I think I said. There you go. So that one it equals a different number, but it equals something is the point, right? It equals a number, even though there's an infinity in the input. Whereas if you look at this other one, where we don't have an infinity in the input, seems like it should just be a normal run of the mill integral, but yet it's undefined. Why is that? Why is it undefined? Why does Desmos say it's undefined? The reason is because if I actually graph that graph, x squared, 1 over x squared, we actually have a vertical asymptote at 0. So that's why this one is a type 2, whereas these two up here were type 1 improper integrals. We clearly have an infinite input in the type 1 improper integrals. This one is very sneaky because you don't see an infinity anywhere. You might think it's a regular integral, like a proper integral, but it's not, because we have an infinity in the output somewhere. Where specifically? At x equals 0, basically. So at x equals 0, if you go to x equals 0 right here, we're shooting up. You can see we have a vertical asymptote, obviously. So it's like it's not as simple as integrating between -1 and +1, because in between -1 and +1, we have 0, and we know that we have an infinite value there. The function is undefined. We have a vertical asymptote. That's the problem. Now, to be clear, if I made this like +1/2, if I went on the other side of if I can integrate this function no problem on the other side of that vertical asymptote, but I just can't have the vertical asymptote be within my bounds. That's what makes it a problem. So there you go. Hopefully that makes sense in terms of some basic terminology, what a type 1, as it's typically called, improper integral, and a type 2 improper integral are. The next question is, how do we actually deal with these? Like, let's start today. We'll just talk about probably the type 1 improper integral, because it turns out this actually, like we said, this actually equals a number, and we just tested it. Now, what I want to show is not every function equals that number, right? So, like, if I change the function slightly, let me get rid of this other stuff. If I change the function slightly to just 1 over x, now it's not defined. So they're not always defined. They may be defined, they may not be defined, and we're going to learn special terminology to talk about that in a second here. But basically, what we'll do, how should I word this? So this is kind of a weird idea to start. So let me actually grab a visualizer to talk about this. Visualization. Just a second. So if we go to like 1 right here, how do we do this? Basically, I guess, how should I word it? Actually, this is not what I want. Sorry, wrong animation. Let me, that's helpful. That's very helpful for Riemann sums, but that's not what I want to look at here. So looking at this is more useful. There we go. So this is just doing a normal integral. So if I go, let me change the function. So let's look at the actual function let's look at this function here to start. So we're integrating. Let me scale this up just so you can see what we're doing. I think you already get it. But basically the idea, we're taking 1, and then again, I can't just, unfortunately, I could type this into infinity, right? And that's what we're actually doing, right? We're going infinitely far to the right. So basically, yeah, that's what we're doing. We have an infinite width, right? I'll just zoom out. We just keep going to the right forever, that area. So this shape, this is a shape with an infinite width, if you want to think about it. And here, hopefully this should make sense. This is why this answer is undefined, by the way. This one is undefined. This is what you should expect, by the way, I would say, is that when you have an area, like whenever you have a shape that has an infinite width, yeah, it makes sense that it would have an infinite area. That's essentially what we're saying here. And if it has an infinite area, that's why Desmos is giving undefined as the answer. There's another word you'll come across for improper integrals. You'll come across the words converge and diverge. What we're looking at now is an example of diverging. Diverging means either the integral goes to infinity, or not necessarily that does that, but like 99% of the time, that's what it is. Sometimes it could also mean that it oscillates around a specific value, or it oscillates around multiple values and never closes it on one. Basically, the limit doesn't exist. We'll talk about what I mean by that in a second here. But you can see this one's undefined, whereas this one, if I just change the function, now it's actually defined. Actually, let me back up. So looking at here, again, don't pay attention to the b value here. Pay attention to the integral, right? I think that's a quirk of Desmos. But here, with this function, the integral is undefined. With this one, it's defined. And with another one, it's defined. And with that one, it's defined. Like with any function smaller than that, it seems to be defined, right? They're different numbers, of course, and even if you go slightly higher, it's still defined. Even if you go slightly higher, still defined. So what's going on here? So basically, your normal intuitions might be, or they should be, I would expect, that this is what mine were when I started, that if we go infinitely far to the right, again, infinite width, we should have an infinite area. So there's no real number. We couldn't say the area equals a finite number, right? It just goes on infinitely. That's That's true most of the time, like right now, but it's not true all the time. Because what's happening here is that if your function, so first off, if your function increases, yeah, definitely goes to infinity, right? This area, as I go to the right, definitely grows forever, goes to infinity. So that is what we would call diverging. Go like the area, the total area, like as you take the b value, and again, it's kind of if I go down here, basically, if you take your b slider and you just keep cranking it up, right? If you just keep cranking it to the left and just keep dragging it to the left, right? Basically, you just keep dragging the slider to the left, or sorry, to the right, I mean. Keep dragging the slider to the right, and you just do that forever. That's essentially what we mean when we say infinity here. But that's what happens. Obviously, if the function grows, if the function gets bigger over time, the area underneath the function will grow to infinity as the width goes to infinity. So that should be pretty obvious. That diverges. If the function increases at all, or if the function increases as x increases to infinity, definitely diverges. The integral does, the improper integral. Even if the function stays constant, that's still true. So here, I actually zoomed in too far for that. I'll just make it 100, make it a bigger example. So even if the function doesn't grow, even if it stays the same, again, this would be like a rectangle of an infinite width. So obviously that's also an infinite area. So even if the function stays the same, it's going to diverge. And even if the function gets smaller, right? 1 over x, if I zoom in here, this gets smaller over time. 1 over x does, right? So if we, so 1 over x gets smaller over time, but it still diverges. However, if we get smaller by fast enough, and fast enough is kind of a hand wavy term in quotation marks, but if we get smaller by like if we get smaller fast enough, it turns out that the speed of us shrinking the height actually overwhelms the speed that we increase the width. Even though the width is going to infinity, the height is shrinking so fast that it kind of cancels that out. That's what's actually going on here. So you can actually end up in a situation where the width infinite grows infinitely, but the height shrinks infinitely, and the height never quite hits zero here, but it gets infinitely close to zero. You can always get closer to zero, right? You can always take your number and divide by 10 to get even closer. So even though the width is continuing to grow as we go to the right, the height is shrinking so much faster than that that it's kind of canceling it out in a sense. And that might seem like a weird idea because, like, you might say, well, it doesn't matter how much the height shrinks. You might think, oh, if the width is going to the right, if the width is growing, if the height is shrinking, we still have a positive height at any point. So doesn't that mean we're always adding a positive amount of area, which means we should go to infinity? Yes, except the last part. So that's the weird thing. So we are always adding a positive amount of area. That's true. So like for example, as I like rewind this down to like 1 and I just start moving the slider, this number is growing forever, right? So it's like if I go to like to rewind, if I go to 10, I get 0.9. If I go to 100, I get 0.99. If I go up, I get 0.999. If I go to 1,000, if I go to 10,000, I'm seeing a pattern here, right? It seems like on the integral, we're getting infinitely close to 1 without hitting it. And that's right. That's exactly what's happening, actually. We will never hit 1. The reason it looks like we hit 1 when we type in infinity, here I'm actually breaking the calculator on Desmos. If I plug in too big of a number, it actually just can't do the integral. It's like the electronics can't represent it in the calculator in the computer. But if I type in infinity, they've programmed it so that it gives the right answer, which is 1. So what does this mean? Does this mean the area under the curve is 1? Not really. That's not what it means. What it really means is that if we keep, because infinity is not a number, we can't literally like have infinity as the upper bound, even though that's how we write it with the notation. We can't act like infinity is not an actual number that we can plug in, so we can't do that. But what we could say, I guess, how should we say? What we could say is that basically if we keep increasing b forever, we take, in other words, the limit as b approaches infinity, then the area under the curve will approach 1. The key word is approach. It never hits 1. It's like 0.9, 0.99, 0.999, 99999. We can have as many as many nines as we want afterwards. But yeah, I'll just say that. As many nines as we want. It'll never hit 1, but it will get infinitely close to 1. So we say that the improper integral equals 1, even though it doesn't truly equal. You got to be careful with the word equal. The limit approaches 1. The limit equals 1. We can say that, but that never means that the actual area is ever 1 with any finite value. just as b grows forever, as the width goes to the right forever, we will continue to add positive area, but we'll never hit 1. That's essentially what we're saying. And again, if that seems like a weird idea, this is something that made it click for me. Think about this: 0.9 plus 0.9 or 0.09. Sorry, sorry, 0. There's a, I don't know why that's glitching here. No, that's annoying. Let me refresh my page. That's a little bit of a glitch, I would say. There we go. So plus 0.09 plus 0.009 plus dot dot dot. Right? What if I just kept doing this forever, for the rest of eternity? I would, every time I add a new number, I'm adding positive. I'm making the total sum of the numbers bigger, right? That's like, there's an analogy. Every time we go to the right by a certain amount, the area does get bigger. We add more area, but the numbers are getting, if height is shrinking fast enough, the chunk of area that we add will get smaller and smaller. If it gets smaller and smaller by fast enough, what will happen? The number will keep getting bigger forever. That's true, right? It'll keep getting bigger forever, but it will never get bigger by fast enough to flip the higher decimal places, if that makes sense. So when the number is getting bigger, because that's what we were talking about before, right? If we're going to the right forever, doesn't that mean that, or how can you say it? Doesn't that mean that we have to add an infinite number of, or doesn't that mean the total area has to be infinity? No, actually. It means that as we move to the right, as we increase our width and take the limit as it goes to infinity, our right bound of our integral, it's true that the area will always go up. But it could also be true, and this is the weird thing, this is the thing that's counterintuitive. It could be true that if the function shrinks fast enough, like the height shrinks fast enough, the chunks of area that we're adding get so small that they really just add on another 9. This is like an analogy. It could be a little different than this, but you're basically just adding another 9 to the end of your number. So that technically makes it bigger, right? You're technically adding a positive amount of area, but at the same time, it's also true that you never hit 1, right? If I just keep adding another 9 to the end of this thing for the rest of eternity, it doesn't matter how long you do it, it will never equal 1. You will never hit 1, right? And that's kind of the key insight here. That's kind of the idea. That's why this works. So even though we get infinitely close to 1, we never hit it, and we say that the improper integral equals 1. What we really mean is the limit as b approaches infinity approaches 1. That's what we mean. So here, hopefully that logic makes sense. That's why these make sense. We're not going to talk about today about how you can actually do these. We'll do that next time. We'll do that tomorrow, probably, unless anybody else has other questions. But we'll cover exactly how to solve type 1 improper integrals and how you can actually go through the mechanics. I'll give you a hint, by the way, before we go, if you want, before we leave today, give this a shot. Basically, wherever you have the infinity, and again, type 1 always has infinity somewhere in the bounds, either infinity or negative infinity, take the limit, or whoops, I already wrote limit as b goes to infinity, and just replace the infinity with a variable. Like usually we use b as the upper bound, a as the lower bound, but you don't have to. You could use r for both. You can use whatever you want, as long as it's not x. X is obviously already taken. But call it a variable, and then see if this makes sense. Solve this integral normally. Solve this integral like you normally would, right? And then what's going to be different is, because normally if this is a number, you'll just get a number after solving the integral. But because this is a variable, you will get your answer to the integral will be a function of b. And then the next question is, what if you take the limit as that limit of that function as b approaches infinity? Does it equal a number, a finite number? In which case, that would be an example of convergence or converging. Whenever we converge, by the way, that means the limit exists and it's equal to a finite number. Or you could get infinity out, and that would be diverge. And that would just be, there is no number. It's like an infinite area. The question doesn't make sense. So give that a try. Basically, that's the only thing you'll do. We'll talk about, we'll pick up next time probably with this problem, and then we'll kind of walk through how to do that. But give that a shot and see if that makes sense. Hope that was helpful. If you have any questions, feel free to drop them in Skool, and I'll be sure to answer them. If you guys have any, I guess, how should I say it? If you guys are not in Skool, by the way, feel free to join. I'm actually thinking it's currently $9 a month, but there's a 7-day free trial, just so you can see to like get your questions answered and see if it's helpful. I'm thinking about making it free though. I'll have to double check, but it might be free honestly by next week. I might make it free. But yeah, give that a shot. Just let me know if you have any questions, and otherwise, I will catch you next time. See you.